finish what we started yesterday. I'd like to give you a day to work on this in class this week, but we got to get through it first. So click and close. Let's take a look. This is where we left off, right? So we were trying to do everything for this, make our new expanded table with a y double prime row. And we had done some things. We had differentiated this polynomial. We found the zeros of the first derivative were at 0 and -2. So those are places where we have zeros of the first derivative. What does that mean in our table then? If I have zeros of the first derivative, horizontal tangents. And then we took the second derivative and it had 1 0 at -1. So -1 was a 0 of the second derivative. Okay, so now we needed to figure out what's going on with the first derivative critical number. So what are our options here? First, if we're going to use the first derivative test, what would we do? We would pick, okay, yeah, pick test points. Like I'd have to, like what, give me an example of what test points I could pick for, to evaluate -2. Okay, I mean, and I could actually use -1 if I want to. How come?
Oh, because then it can do both of them.
It could, right. -1, because I have to pick points between the first derivative critical numbers. Now, I don't care about the second derivative. You see what I'm saying? So -1 would actually work, right? And I could pick another one over here, so I could use this guy, and I could use one like at -3 or something, right? That'd be fine. That would work. And for 0, to pick points bracketing the critical number, the first derivative critical number at 0. So I'm just going to do that. I'm going to call those critical numbers, and then -1, I'm just going to do this. I'm going to call it that, right? So it's a second derivative critical number. And we could pick another one like at +1 or something and check the signs of the first derivative. That would work, right? So let's do that real quick. Let's use those critical numbers. What is the sign of the first derivative at -3? And we'd use the factored form. I got two factors. At -3, I'm going to get positive or negative for my first one. Positive times, so I get negative. How about at -1? I'm going to get positive times positive, okay? So we would, oops, I put those in the wrong spots, didn't I? Those are supposed to be there and there. Okay, so what's going on there then? Decreasing to increasing, so what is it? It's a smooth valley, yeah. So we know it's doing. It's doing that, right? We've already got a critical number there. What about at +1? What's the sign going to be? Negative times, so negative. And so what's that? That's a peak. Okay? All right, so we could do all that stuff. That was fine. But I had to pick a bunch of extra points to do that. Turns out I didn't need any test points if I used the second derivative test. Here's the second derivative test. We can forget about all this stuff. We can just cross all this stuff off. And instead, we can just find the derivative or the sign of the second derivative at each of our first derivative critical numbers. What is the sign of the second derivative at -2? Positive, okay? Tell me how that information goes together to tell me that it has to be a minimum. A combination of a 0 first derivative and a positive second derivative guarantees I have a smooth, how come? Because it's concave up with a horizontal tangent. What else could it be? Right? If I have a horizontal tangent and it has positive concavity, that means the tangent line sits above or below. If it's below, right? Positive means it's bowl up, so the tangent sits below. So think about that. If a horizontal tangent sits below the curve, and then doesn't that mean it's a minimum? Right? You see how that works? That's the second derivative test. Much more efficient than the first derivative test because I don't even have to find any test points. What do you think is going to happen here? Make a prediction. What's the sign of the second derivative going to be there? Has to be negative because a horizontal tangent and negative concavity means I have downward concavity in a horizontal tangent. That has to be a minimum, right? And we can verify it. At 0, the sign of the second derivative is going to be negative times positive is negative. What do you know? Okay. And look at this. I killed 2 birds with 1 stone because I found the signs of the second derivative surrounding its only critical number. What can you tell me about this point at -1? My critical number of the second derivative, the place where the second derivative was 0. What's going on there? It's an inflection point because it's a transition in sign for the second derivative. So look at that. We got all that information with no test points. Yes?
So with the second derivative test, you put the critical numbers into the second derivative?
Yes. Yeah, you put the first derivative critical numbers into the second derivative, and the sign of the second derivative will tell you what those were. Now, it only works for 0 first derivatives. It's not going to work. Does that make sense? It's not going to work for if I have a sharp corner, then it can't have any concavity at that point. Does that make sense? Okay. So that wouldn't work. Then, okay, so if the second derivative fails, you default to what test? First derivative test, which always works, but it's just more work.
Even if
right?
there's only 1 point that failed, you still use the first derivative?
Well, then, no, you could, I mean, for that 1 point, you'd have to use the first derivative test. Maybe for other values, second derivative test would work, and then use it. The other thing about the second derivative test, though, is that it requires a second derivative, right? So if you were trying to find, for example, what if all you wanted were extrema, peaks and valleys? Would you want to use the second derivative test? It depends. If the second derivative is really easy to take, then for sure. Like if it's a polynomial, the second derivative is a piece of cake. So why not just take the second derivative? But if I had a quotient with radicals in it and stuff, I mean, you're probably not going to want to take a second derivative, right? Then you would just use the first derivative test and avoid having to do all that hard calculus. Okay? So you're going to be pragmatic about it. So this is, okay, so some stuff we need to know then. And this is right out of your textbook. Important definitions. So definition from yesterday, definition of concave up and concave down. What about concavity? So we just said, now, and this is important here, if f is a function that's continuous on a closed interval and differentiable on the open interval. So if it's differentiable on the open interval, what does that mean? Everything but the endpoints, but what does the differentiable part tell you? Think what that means, because people get confused by that sometimes. And I can remember, like this was sort of, this was something that was, when I first saw this out, okay, that was helpful. If f is differentiable on open interval from a to b, what does that tell you about the derivative? Say it again. It exists every place, and so it'd have to be continuous, right? What are places where a function would not be differentiable? It's not differentiable. Just means take the derivativable, right? That's what differentiable means. I'm able to take the derivative every place, so it means the derivative exists everywhere, right? Okay, so when we say something like the function is differentiable on that open interval, if I can take the derivative everywhere, can I have any sharp corners? No, right? I can't have sharp corners. So it means if there's no sharp corners, and we know that the function is continuous on the closed interval, so a lot of times in calculus, our textbook doesn't do this, but every class I took in college, they use this terminology. They said if a function, if f is continuous on, and this is both in grad school and undergrad. There's never a class where they didn't use this exact terminology. If it's continuous on the closed interval from A to B and it's differentiable on the open interval, well, think what that means. Continuous means I can draw it without picking my pen off the board. Differentiable means the derivative exists, so there's no sharp corners. The combination of those things is, we could say instead, f is smooth on A to B. Doesn't that make sense? And it is descriptive. It's a smooth curve. It doesn't have any jagged. You can't ever scratch your hand on it if you're rubbing your hand on the curve, right? It's always going to be, it has always rounded corners every place. You can't have any sharp corners, and you never pick your pen off the board. So it's a smooth function. It combines those two elements. You might hear that terminology again. I'll probably say it again. So if the function is smooth between A and B, then the function's concave up wherever the graph of f lies above tangent to the curve, right? Visually, that's what concave up, and we talked about that yesterday. The function's concave down if the function lies below its tangent lines for every value on that interval, right? Tests for concavity, you already know them. If the function's continuous, and if both the first derivative and the second derivative exist on the open interval, right? So that means it has to be smooth, and the second derivative also has to exist. Then, wherever the second derivative is positive, we know that's positive concavity, it's upward concavity. Wherever the second derivative is negative, it's negative concavity, it's downward concavity, right? And that's all the stuff we talked about yesterday. Any questions on that? Okay? Here's another piece of terminology that you'll run into in calculus, maybe differential equations classes for sure. When f prime and f double prime both exist on an open interval, then we say the function is twice differentiable, because I can take the derivative 2 times and it's going to work everywhere, right? It's differentiable. If I could take a third derivative, it would be thrice differentiable, and so on, right? We rarely take third derivatives, though. What's an inflection point? Okay, so I added some notation to this. This is the book stuff, and I just added a couple little things. Suppose f is a function that is differentiable on an open interval, the open interval a to b containing some point c. Well, in other words, the tangent line exists at c, right? That's what we said yesterday. Tangent line has to exist. If the concavity of f changes at the point c, then we say that's an inflection point. And we know how to look for that in a table. It's just where the sign of the second derivative transitions, because that's what would cause a change in concavity, flipping signs of the second derivative, right? Give me thumbs. That all make sense? Okay? So suppose f is a function that is differentiable on an open interval containing c, and at c we have an inflection point. Then there are 2 possibilities, and one of them is kind of rare. Either the second derivative is equal to 0, or it is possible that the second derivative doesn't exist at c. That's kind of a rare thing. It almost never happens. I mean, it's kind of a dumb thing to say in math, because if it's possible, we have to consider it, right? But you really don't run into problems where that happens very often. It's a little bit weird. I just made one up. I haven't done this before, but I just made one up because I want to show you an example. You don't see it very often. But there's one where the second derivative we'll see is undefined, and that is an inflection point. So I want you to see, I mean, you're not going to see this very often, but don't say I didn't show it to you at some point, right? You see this in college, maybe. Here's an example. Piecewise function, f of x is defined as x squared, where x is less than 0, and negative x squared, where x is greater than or equal to 0. Okay? What's the derivative function going to be then? How do we differentiate a piecewise function? It's been a while, but just use your intuition. What do? Yeah, just differentiate each piece, right? What's the derivative of x squared? 2x. Okay, so on the domain where x is less than 0, we get 2x. When x is greater than or equal to 0, we get Negative 2x, yeah, good. And okay, so now here's the thing though. So there's our derivative. Is the derivative defined at 0? Okay, I'm seeing people shaking their heads. Think hard about this now. Is the derivative defined at x equals 0? It is, you're right. If you said no, you were looking at the blue graph probably, weren't you? Because the blue graph has a sharp corner. What is the blue graph though? It's a graph of what? Is it the function? It's the derivative. Okay, well, derivatives don't exist where the function has a sharp corner, right? Okay, so the derivative does exist at 0, and we can see that it does because the function is continuous and it has a tangent line there, right? What is the value of the derivative at 0? 0, okay, and it works because as we approach 0 from the left, the derivative approaches a value of 0, and as we approach 0 from the right, the derivative approaches a value of 0. So we're okay, right? That works. The tangent line would be horizontal at 0. Yes, it would. And you can see we have an inflection point there, don't we? Right, a place where the derivative is 0, but it's not a minimum nor a maximum, right? Okay, now, what's the second derivative going to be? When x is less than 0, I'm going to get 2, right? When x is greater than or equal to 0? Okay, could I include 0 then? No, and we knew that was going to happen. How come? Because there is a sharp corner in the first derivative, and the second derivative is the derivative of the first derivative. So if the function we're differentiating, first derivative, the blue function, has a sharp corner, then the new derivative function, the second derivative, has to be undefined there, and it is. Right? Look what happens. Okay, we no longer can put an equal sign there because the second derivative now is either positive 2 or negative 2. Look, I have to have open endpoints though, don't I? Because it's not defined at 0. Okay, but you can look at the original red graph, and is there an inflection point at 0, 0? Obviously there is, right? You can see that the concavity changes there. So that's one of those rare examples where you actually can have an inflection point at a place where the second derivative is undefined. Right, Mr. Haygood?
Yep.
Okay.
Remember these?
I do. Those are great. Yeah. Thanks.
It's like I haven't seen that for 2 years.
Yeah. All right. Okay. So notice the wording in the theorem. If you know that C is an inflection point of f, then the second derivative at f either is 0 or it doesn't exist, right? Okay. The converse is not necessarily true. You get that? That's often the case in math. You can't generalize and say that the converse is true. Just because the second derivative is 0, does that mean it's an inflection point? No, it does not. And we'll look at some examples today where that fails. Just because the second derivative is undefined, does it mean it's an inflection point? No, it's usually not. Okay? So then what's our strategy? Finding inflection points of a function f. So this is the part where this is what we just started working on. What are we going to do? We're going to find all the numbers in our domain of our function for which the second derivative is equal to 0 or where it doesn't exist. Okay, now there's something else. I think they kind of left something out there though. Because for us to be able to take a second derivative, the first derivative needs to be defined, right? Okay. So what else has to be true? The function must be differentiable at C. Okay. So f prime of C has to exist. So then we just use the test for concavity to determine if the concavity is flipping, and that's what our tables do for us. That's it, right? You see how great these tables are. They take all these wordy theorems and you can just summarize them all in one really elegant little table. Okay, there are some things though, let's see. Oh, there's something got left out. What? Oh, there it is. Yeah, never mind. Okay, so there's our second derivative test we've already talked about. Okay, second derivative test. If we have a 0 of the first derivative, then we can check the sign of the second derivative to see what kind of animal is that. Is it a peak or a valley? So sometimes the second derivative test can't be used, or it gives no information though. It fails. Where does it fail? Well, one place it could fail is if the second derivative doesn't exist at a critical number. If it doesn't exist, it can't tell us anything, right? So it fails. And remember, the second derivative can't exist outside of the domain of the first derivative, right? If the first derivative doesn't exist, how could you differentiate it at a place where the first derivative doesn't exist, right? So do you see that as the domain, like the domain of the function could be, we could have a certain domain for the function. If the domain of the first derivative is smaller than the domain of the function, that can happen. Could the domain of the first derivative ever be bigger than the first? I can't talk. Could the domain of the first derivative ever be larger than the domain of the function? No, it can't. Right? You can only take a first derivative where the function exists. So the domain of the first derivative is always less than or equal to the size of the domain of the function. Same would have to be true for the second derivative, right? Second derivative, the domain of the second derivative would always be equal or smaller than the domain of the first derivative. You get the idea. Okay, what else could happen? If the second derivative exists at a critical number but equals 0, then that also doesn't tell you anything, right? That doesn't have a concavity, and so you can't use the second derivative test. So it gives you no useful information. And in either cases, you would just revert back to the first derivative test, and that would answer the question. Okay, so the one we just did, this is what a full table would look like. You don't really need to do more than this, right? We could take limits. What's the end behavior going to look like for this? Show me with your arms. Yeah, right, negative odd behavior, right. So it's up to the left, down to the right. So the limit at negative infinity is positive infinity. The limit of the function at positive infinity is, oh, that's supposed to be negative infinity, isn't it? Whoops. Right? Okay. And then we've got these three ordered pairs. All we need to do, we know we have, is use the second derivative test to figure out what's going on at the first derivative critical numbers and to determine that the second derivative critical number is an inflection point. So it's a pretty lean table. We don't have to do we don't need any test points if you use the second derivative test. Give me 1 to 5 on that. Is that making sense? Kind of the logic behind all this stuff? Okay, let's keep going. Let's just try some more of these. It just takes practice. So how about this one? We have a function. It's polynomial, so we're celebrating. Polynomials are really easy to work with, right? What do I do? What's my domain first? Negative infinity to infinity. There you go. Do I have any symmetry here I can exploit? No symmetry. I have both even and odd exponents in my polynomial, so no symmetry, unfortunately. So what's the next step? First derivative. What's my first derivative? Okay. Could we factor that? What would the magic numbers, is that going to factor? Not going to factor, is it? We'd have to find magic numbers that multiply to 15 and add to 4. That's not going to happen, right? So it's not going to factor easily. So we want to find the zeros of this thing. How would I find the zeros? Set equal to 0, and how would I solve that quadratic equation? Quadratic formula, okay. Where do I start with the quadratic formula? But I mean, recite the quadratic formula for me. Right, okay, so what part of the quadratic formula do I want to always kind of pre-calculate? The discriminant, the part under the radical, because it tells me right away if I'm going to have real solutions, right? If the discriminant, if the part under the square root is negative, there's no reason to go do all this to do anything, right? Because I'm not going to have any critical numbers. This derivative is nowhere undefined. Well, what is the discriminant, positive or negative? B squared minus 4ac. 4 squared minus 4 times 15. Positive or negative? Negative for sure, right? So because the discriminant is less than 0, so no real zeros. I get no first derivative critical numbers. Okay, well, how about my second derivative? What's the second derivative? Okay, so what's the 0 of the second derivative? Which is negative 2/3, right? Okay. Everybody agree with that? Subtract 4, divide by 6. Okay. So then this is a pretty easy table. We only get one critical number. Whoops. And it's a second derivative critical number. It's where the second derivative equals 0. So the only thing I could, are there going to be any extrema? Could there be? Give me thumbs on this. Is it possible there are any extrema? That's right. How could you have an extremum if there's no critical points? Because all extrema necessarily exist at critical numbers. They have to, right? Not all critical numbers are going to be extrema. Some could be false alarms, but you can't have an extremum without an associated critical number. So this thing is never going to have a peak or a valley. So what that means is it's going to be monotonic, increasing, or decreasing. What do you think that means in math? If I say a function's monotonic increasing, always increasing, right? Or monotonic decreasing. It's either always increasing or always decreasing, one or the other. Okay, so how could we find out, by the way? I mean, we don't even necessarily need to do, what's kind of cool about the table is you can infer a lot of stuff. Let's say we want to find inflection points too. What's the one thing we would have to do on this table to find an inflection point? I know I have a 0 of the second derivative at negative 2/3, but for that to be an inflection point, what would have to happen? It'd have to change concavity. So what's that mean I have to do then? I got to test some values, don't I? I got to test some values. So I could pick something like 0. That'd be an easy one, right? We could pick 0 as a test point. What's the value of f double prime at 0? 4, so it's positive. I could pick something like negative 1. At negative 1, it's negative. Aha. So that is an inflection point, isn't it? Right? If I'm going from downward concavity to upward concavity, could you guys tell me without even doing a calculation, what is the sign of the first derivative every place? What is it? It is. How come? Think about what the picture has to look like. If I'm going from concave down to concave up, doesn't the thing have to be increasing? Is that true? That's not true. What did I just say that for? Yeah, that's not true at all, is it? I could do this. Couldn't I do, I could do that and it could be decreasing. That was a dumb thing to say. Yeah, that didn't work at all. Sometimes you can infer stuff, but not that time. You see my point? The concavity didn't really impact it there. So what would I have to do to find if the function's always increasing or decreasing? How many points do I need to check? I mean, if the derivative is going to have the same sign everywhere, so how many points do I need to check? Just one. Just check the most convenient one. I could check any of these. 0 would be the easiest, wouldn't it? What's the sign of the first derivative at 0? I get 5, which is positive, right? So this tells me that this thing is increasing everywhere. Okay, so it would have been that first picture that we drew.
Why do you check it with the first derivative?
Well, because if it wanted to know, like for example, if they wanted to know where the function, on what intervals is it increasing or decreasing? Okay, the sign of the first derivative would be increasing everywhere. Yeah. And decreasing nowhere. And so we just need to know if this is positive or negative. What's it doing every place? Okay. Okay, so we got a picture of this. If we did want to graph it, there it is. That's what it does. Okay, make sense? Concave down, concave up, increasing everywhere. How about this one? This is a quick one, but there's something really important that comes out of this. Super easy function to deal. We know exactly what that looks like, right? F of x equals x cubed. Domains everywhere, right? Obviously. Does it have symmetry? What kind of symmetry, odd or even? It has odd symmetry, so it's going to have rotational symmetry about the origin. We know that. What about our derivatives? First derivative is 3x squared. Second derivative is 6x. Okay, where's our only first derivative critical number? 0, yeah. So at x equals 0, we have a 0 first derivative, which means what? Has to be a horizontal tangent. Let's try the second derivative test. What's the value of the second derivative at 0? Okay, you see the problem. The second derivative fails to tell us anything. So the second derivative test failed there. It didn't give us a sign. Second derivative test only works if I get a 0 first derivative and a plus or a minus. So what would we do then? Just revert to the first derivative test and pick some test points. So we'd pick something like -1 and +1. What's the sign of the first derivative at -1? Positive. How about at +1? Positive. Okay, so what is this thing then? It's an inflection point. It's an inflection point, right? Because we know that if this thing is increasing on both sides, there's only one thing that this thing could be doing, right? If it's increasing all the way and it's concave down on this side, or actually we don't know it's concave down, but it has to be. Has to be. The only thing it could do is that. Agreed? If you have a 0 of the first derivative and a 0 of the second derivative, there's only two possible things that are going on there. Either it's an extremum or it's an inflection point. If it's not an extremum, it's an inflection point. So here's an example of where we could infer without even doing a test. Can you tell me what's the sign of the second derivative guaranteed to be to the left of that 0? It's guaranteed to be negative. How about on the right side? Positive. We could check it, but we don't need to. If I plug a negative number in, I get a negative output. If I plug a positive number in, I get a positive output. Do you see why it has to be that way? I defy you, I double dog dare you to draw the shape of a graph that has positive first derivative on either side of that horizontal tangent that doesn't have downward concavity to the left and upward concavity to the right. You couldn't do it, could you? Right? There's no way you could possibly draw a piece with upward concavity that's going to be tangent to that yellow line and be below the graph. You just can't do it. Not in this universe, right? Make sense? Okay, so what about if we did something similar for x to the 4th? F prime of x would be 4x cubed f double prime of x would be 12x squared. So same situation, right? We know we're going to have a 0 of the first derivative at 0, and we're going to have a 0 of the second derivative. Okay, so again, this has to either be an inflection point or a minimum, right? So we always defer back to the first derivative test. Okay, do you have to? We might as well be consistent and do that. But could I work on the second derivative row here? I could, right? What if because the second derivative is an even function, it's always positive valued, right? Or it's non-negative, it's never negative. Agreed? So I know this is going to be true. What's the only way I could possibly draw a curve, a smooth curve, that has a horizontal tangent at 0 and upward concavity to the left and the right? I mean, it's got to have a minimum, doesn't it? Doesn't it have to do this? And we know it's even symmetry, so it all falls together, right? You see my point, though? Did we technically have to revert back to the first derivative test? No, we didn't have to. We could just fill in the second derivative row and get everything we need on the function. If we had done the first derivative test, what would I have found? What would that have been? Negative, and that would have been positive, guaranteed. Okay? How are we doing? Is that making sense? Okay? Let's see. Okay, so why did I pick this one? Just a second. I think I know why, because I wanted you to solve a cubic, yeah. Okay, so polynomial, right? Agreed? What are the characteristics of a polynomial? The coefficients all have to be what? Real. And the exponents have to be what? Well, I need more than that. Well, okay, that's not specific enough. Not all rational numbers would work if it's going to be a polynomial. If it's a polynomial, what do all the exponents have to be? They can't be fractions. The whole numbers is right. They'd have to be whole numbers. Yeah, 0, 1, 2, 3, 4, etc., right? So positive or non-negative integers, so whole numbers. So that is a polynomial. So we know this thing is going to be continuous everywhere, right? It's super well behaved. And we always know polynomials are going to be smooth, because if I differentiate a polynomial, what do I get? Another simpler polynomial, right? So all levels of derivatives will always be defined everywhere, right? So let's differentiate this. What's f prime of x? X cubed, good. Minus okay, good. So we need to find zeros of that thing, right? Okay, well that's a little bit tougher, right? Because there is no cubic equation to use, or cubic formula, like we have a quadratic formula, right? Okay, but this is one hopefully you see it's going to be easy to factor. How come? It's been a while, but this is important to know. Well, you could use synthetic, and that would be like we could use the rational root theorem. But you can factor by grouping. That's the point I want you to see. How can you look at this and immediately tell that you can factor this by grouping? Because you don't want to waste time with the rational root theorem, right? Right, there's a test. Remember this test we talked about a couple years ago? You probably don't, I understand, but I'm going to remind you so you will remember it. We got two groups here, right? So there's two things. If you can see two patterns, factoring by grouping is guaranteed to work. Remember, one's the ratio test. if the ratio of the first two coefficients equals the ratio of the last two coefficients. So in other words, does 1 over negative 4 equal negative 16 over 64? And the easiest way to tell is just cross multiply. 64 equals 64, so yes. So we pass the coefficient test, right? The other test is the exponents have to drop by the same amount in each group. How much do the exponents drop in group 1? By 1. How much do they drop in group 2? By 1. Okay, so you pass both those tests, it's guaranteed to factor by grouping. And it's just a visual test you can do really quick. And factoring by grouping is so quick and easy, we'd much rather do that. So first group, a quick reminder. What do I do with factoring by grouping? Factor out the GCF, which is x squared. Good. So I factor out an x squared, which leaves behind what binomial? Yeah, x minus 4. Then remember, you've got this plus sign in the middle that separates the groups. Now remember how to do this. If we know factoring by grouping is going to work, this is just going to fall into place easily. But the pattern we always use is we need to have the same binomial in both groups because that's going to be a common factor. So you always, in group 2, you always start with the binomial first because it has to be the same. And then you just answer the question, what needs to be there? Negative 16. Good, so then we get x minus 4 times what's left behind? X squared minus 16. And remember, all this stuff is, what are we trying to do here? We're trying to set all this stuff equal to 0 to find the 0. So what are they? I get plus or minus 4 and 4, so just plus or minus 4. Make sense? Are we out here in like 1 minute? Okay. We'll wrap this one up later, but